Hello everyone. So welcome to the first lecture video on chapter 15 for Pure Chemistry, the Reactivity Series of Metals. Now this will be a series of 3 lecture videos that you will need to watch while I'm on course. So this is the first of the 3 videos. Now the first video should be quite straightforward and simple because it actually relates to a topic that we started under chemical bonding and structure. So if at any point you are lost for the first part of today, you may wish to go back to Chemical Bonding and Structure, Chapter 4 and 5, Part 3, where we learn about metallic bonding or the giant metallic lattice. So for the first 10 minutes or so today, we will be revising the giant metallic lattice and also the general properties of metals. Now, why are we studying metals? I'm sure you can see in the periodic table, there are metals and non-metals. And metals form the majority of all the elements. So about 60 to 70% of your elements are actually metallic. Hence, metals are very common, very useful, very important for us. All right, now let's jump into the structure of a metal. Of course, you have learned this. The structure of a metal is called the giant metallic lattice. So the idea here is the valence electrons in the outermost shell of metal atoms can actually be lost to form delocalized electrons, which are free to move to conduct electricity. Okay, so the idea is the giant metallic lattice consists of a lattice of positive metal ions surrounded or in a sea of delocalized electrons. Okay, this should not be unfamiliar to you. We have done this in chapter 4 and 5 under metallic bonding. Now, a very typical O-level question would give you the diagram. So this is what the giant metallic lattice would look like. So it points to the delocalized electron as well as the metal cation. So you can see that the metal cations are arranged in this regular structure called the lattice, and the lattice is itself surrounded by a sea of delocalized electrons. And the key thing here is that the delocalized electrons, they can move freely. And this freedom of movement of the delocalized electrons is what allows it to conduct electricity in all states. So for metals, they can conduct electricity in the solid state as well. Okay, that is actually quite rare. Only metals and graphite can conduct electricity in the solid state. Okay, if you recall from bonding and structure, ionic compounds, even though ionic compounds contain ions which are charged, ionic compounds cannot conduct electricity in the solid state because the ions in an ionic lattice are not free to move in the solid state. However, for the giant metallic lattice, they already have delocalized electrons that can move freely to conduct electricity. And hence, one of the first important properties of metals. Firstly, metals generally have high densities and high melting and boiling points. Now, this is generally true, but there are exceptions, and it's extremely important to learn the exceptions. So, the exceptions to this rule that metals have a high melting point is group 1 metals. Now, group 1 metals are like sodium, potassium, and so on. These are generally called the alkali metals. We will see why very shortly. But group 1 metals, they do not follow the usual trend of melting point, boiling point, and density. Because group 1 metals, they have low melting and boiling points. So for instance, sodium actually melts at 98 degrees Celsius. That's pretty low. All right, compared to other metals like iron. Iron will need more than 1000 degrees Celsius to melt it. That's the difference. So sodium melts at 98, potassium melts at 63 degrees Celsius. So again, you can see the melting point actually decreases down group 1. So potassium, which is below sodium in group 1, okay, further below sodium in the group, actually has a lower melting point. All right, and these are really quite low melting points. Next, alkali metals in group 1 have low density, meaning they will float on water. So potassium and sodium are able to float on the surface of water. All right. Now, another notable exception is mercury. Mercury's chemical symbol is Hg, which is rather unusual because it's quite different from its name. Now, mercury has a high density, but mercury has a low melting point. In fact, mercury is a liquid at room temperature. This is quite interesting because in the whole periodic table, there are only two elements that are liquids at room temperature. Mercury is one of them. The other element, which is a liquid at room temperature, is bromine, which is in group 17. It's a non-metal. So it can be said mercury is the only liquid metal at room temperature. All right. So these are the exceptions to the rule that metals have high melting points. All right. Now, metals generally have high melting points except mercury and group 1 metals. And the explanation is over here. It should look familiar if we have gone through this in metallic bonding in chapter 4 and 5. So I would advise us to read this explanation, ensure we understand it, and ensure we can apply it in a question to explain why metals have high melting points. Next, we move on to the point that metals are good conductors of electricity and heat. Now, this one, there are no exceptions. All metals, no exceptions, are good conductors of electricity and heat. And this has to do with the free moving delocalized electrons in the giant metallic lattice. So the delocalized electrons are free to move when you apply a potential difference, a PD, across the piece of metal. Now, how do you apply the potential difference? Typically, you wire it up to a cell. Okay. Now, in terms of conducting heat, why are metals good conductors of heat? It also has to do with the delocalized electrons being free moving, because the free moving delocalized electrons can collide together. During these collisions between the free moving delocalized electrons, there is actually very rapid transfer of thermal energy by conduction. Okay, so it's important to note that all metals are good conductors of electricity and heat. There are no exceptions. The next property, which we have gone through before, is that pure metals are malleable and ductile. So as a revision, malleable means it can be molded into different shapes. Okay, so malleable starts with M, molded also starts with M. It is molded into different shapes without breaking. So metals, pure metals, they can actually be molded into different shapes, be it ingots, rods, cylinders, cubes, without breaking. Now, the word ductile means it can be drawn, pulled into thin wires without breaking. Okay, so all in all, it has to do with the fact that pure metals are able to change shape easily without breaking. And what's the explanation for this? Now, in a pure metal, the atoms should be all of the same size because they are the same element. Because the atoms are of the same size, the atoms will be arranged in orderly, regular layers. And therefore, when a force is applied, the layers of metal atoms are able to slide over one another easily, and hence is able to be molded or beaten into sheets without breaking. Okay, now that's for pure metals. Now, this is not necessarily desirable in an actual application of metals. You may not want the metal to change shape so easily. You may not want the metal to deform so easily. So, how then do you achieve greater strength? To achieve greater strength, we will use a mixture of a metal with other elements, and this is called an alloy. Now, an alloy is a mixture of a metal with other elements. Now, the other elements need not all be metals. We have gone through this before in chapter 4 and 5. If you look at steel, which you should know very well, steel is an alloy of iron metal and carbon. Carbon is a non-metal. All right. So it is possible to alloy a metal with a non-metal. But this, importantly, is a mixture. It does not involve iron and carbon reacting together. It's not an ionic compound, it's a mixture. You are just physically mixing the two elements together. There is no bonding between the two elements. There's no new chemical compound formed. So steel is just a mixture of iron and carbon. They're simply physically mixed together. Okay, now other common alloys, bronze is copper and tin mixed together. Brass is another common one to learn, copper and zinc. Okay, now the last one to learn is stainless steel. Now, stainless steel is particularly important because stainless steel contains chromium. Chromium makes it resistant to rusting. So, iron typically can rust in the presence of water and oxygen, which is all around us. There's water vapor in the air, there's also oxygen in the air. So, if left out in the open, iron will rust. However, stainless steel ensures that it's resistant to rusting. How does this work? It's because of the chromium. Chromium is able to react with oxygen in the air, and this forms chromium oxide, which is a layer that coats the steel, the stainless steel. And because of the chromium oxide layer, it protects the iron beneath it from rusting. Okay, so we will come to this again in the third lecture video when we look at different methods to prevent rusting. Now, let's recap. Do alloys have a fixed melting and boiling point? Explain. So as you can see, alloys are mixtures. Mixtures are by definition impure, not pure. Mixtures are impure, and therefore they do not have fixed melting and boiling points. This means that alloys, they will melt and boil over a range of temperatures. Okay, so melting over a range of temperatures is the same as saying it does not have a fixed melting point. And this is definitive, conclusive evidence that alloys are impure. So if you were asked to tell whether something is pure or impure, we need to look at its melting or boiling point. Okay? Now, as mentioned, pure metals are very malleable. They can be easily changed in shape. That's not good. Actually, you would want your metals to be harder and stronger. And that's the main reason why we use alloys. We use alloys very commonly. Number one is because alloys are harder and stronger than the pure metal. This is the primary reason. Now, secondary reasons include the alloys may be shinier. It looks better. Or like stainless steel, the alloys are more resistant to rusting and corrosion. All right. So, why are alloys stronger, harder, and less malleable than the pure metal? Now, you need to remember the three Ds. The atoms in an alloy are of different sizes, different sized atoms, because they have two or more different elements which are mixed together physically. So, you can already see in the diagram you have two different sizes of atoms. So different sized atoms, and this breaks up or disrupts the regular layered arrangement of atoms, and therefore it's difficult for the layers of atoms to slide over one another easily. Okay? So this is the main explanation which explains why alloys are harder, stronger, and less malleable, less easily deformed than the pure metal. Okay, and this is actually very good for construction. If you wanted to use the alloy for construction sector, you need something that is strong, hard, and can withstand deformation. You do not want it to deform. Okay, now particularly steel is an important alloy to learn. Steels in general are alloys of iron and other elements. Now the other elements always includes carbon. All right, there's always carbon. So iron is alloyed with carbon. So we have low carbon steel, high carbon steel, stainless steel, and manganese steel. Now, what's very important to take note again is chromium. Chromium makes it resistant to rusting. Okay, and this is due to the formation of the chromium oxide, Cr2O3 layer. So if you recall, chromium oxide, Cr2O3, has chromium in the +3 oxidation state. All right. So when chromium reacts with oxygen, it forms Cr2O3. And this is a layer on top of the steel, which protects the steel from rusting. Now, you notice there's low carbon steel and high carbon steel. This differs in terms of the percentage of carbon. You notice that the higher the percentage, the stronger the steel becomes. So high carbon steel is stronger, but it's also more brittle. That means it will break easily if a force is applied to twist it. So, for example, knives are made of high carbon steel because it's very strong. It can withstand heavy weight and forces acting on it. But if you use a force to twist it, it will immediately snap very easily. So, what we notice is the addition of more carbon. So, more carbon, stronger, but also more brittle. So it's more vulnerable to breakage. Okay, so that's the idea behind the percentage of carbon and what properties the final steel alloy would have. And this concludes the first part of this lecture video, which is on physical properties of metals, metallic bonding and the metallic lattice, and alloys. Okay, please pause the video here and rewatch if you are still unsure about alloys. Remember, you will need to be able to answer explanation questions. Why metals have high melting points, why metals can conduct electricity, and finally, why are alloys harder and stronger than the pure metal? Okay, now we will move on to the chemical properties of metals. Now, when we talk about chemical properties, we are referring to chemical reactions of metals. To understand the reactions of metals, we need to first understand that not all metals are equal in terms of reactivity. Some metals react violently, even explosively. Some metals are very unreactive. So, what makes them reactive? What makes them unreactive? How do you predict that? Is there a rule? So, now we shall learn the reactivity series formally so that we can formalize our understanding of how we could predict if a metal were to be reactive or unreactive. Let's start off from history. If you studied history, you will know that history has progressed in terms of ages, right? Ages. So human society has defined the Bronze Age many, many thousands of years ago. And then we had the Iron Age. So you notice the eras of human history have always been defined in terms of a metal, iron, or an alloy, such as bronze. So this really shows you that metals have been central, have been very crucial and important for human society development. Without metals, we just cannot imagine modern society. So why is it that we have a Bronze Age? Bronze is made of copper and tin alloyed together. So why would we have a Bronze Age and Iron Age? Why is there no Sodium Age, Potassium Age? In fact, the shocking thing is sodium, which is so commonly tested in exams, potassium, so commonly tested in exams, one of the first elements you learnt. Potassium was discovered recently, you know. Of course, it sounds like a long time ago, 1807. 1807 is about 200 odd years ago. That's quite recent. Considering the Bronze Age, you're talking about 2000 years ago. All right. So comparing potassium and bronze, why is potassium discovered so recently, whereas bronze, which is an alloy of copper and tin, was made so long ago? It has to do with their reactivity. So now let's dive into the reactivity series. Now you have seen this with me under the chapter on acids and bases. The reactivity series is a series that ranks the metals in order of chemical reactivity, with the most reactive metal being on top. So the top of the reactivity series is the most reactive metal, whereas the bottom of the reactivity series, the least reactive metal. So when you're asked for position in the reactivity series, we need to talk about top of the series and bottom of the series. So you can see here, this is the series: potassium, sodium, calcium, magnesium, aluminum, carbon, zinc, iron, tin, lead, hydrogen, copper, silver, and let's add one more at the bottom: gold. Now, gold is really unreactive as a metal. So right at the bottom of the reactivity series is one of the least reactive metals there is. Okay, so you notice a few things. Number one, we have inserted carbon and hydrogen into the series. I believe you recall from our quizzes so far, there's a good reason for putting hydrogen into the series, because for hydrogen, even though hydrogen is a non-metal like carbon, for hydrogen, that it's put into the series because only metals above hydrogen can react with acids. Metals below hydrogen like copper, silver, gold, they do not react with acid at all. So you cannot make copper 2 sulfate by putting copper into sulfuric acid. It wouldn't work. So like in salt prep, I've told you, when you hear copper 2 sulfate, copper 2 something, copper 2 should sound alarm bells in your head. Because to make a copper 2 salt, you can't use copper metal with acid. Because copper metal is below hydrogen in the reactivity series, copper metal is unreactive with acid. All right. Now, we shall quickly move on to 3 reactions of acids. The first one is metal with cold water. Now, metal with cold water forms the metal hydroxide. So it's the hydroxide that's formed, and hydrogen gas. Now, that's unsurprising. I said this during acids and bases. Metals are always linked with hydrogen gas. If you have hydrogen gas produced, the previous step, the previous reactant must have been a metal. All right. Now, over here, I'm looking at metal reacting with cold water. Now, cold water refers to room temperature water. Without any heating, no need for Bunsen burner. Under these conditions, only the top 4 most reactive metals can react with cold water. So as you can see, this is actually on page number 9. I would like for you to actually circle the 4 metals, the top 4 most reactive metals will react with cold water. Do circle it so that at least you remember which metals can react with cold water and which metals can't. Okay, so we shall start with potassium. Potassium is right at the top of the reactivity series. Therefore, potassium is the most reactive. Being the most reactive, it reacts very violently with cold water to form potassium hydroxide and hydrogen gas. So remember, it's the metal hydroxide that's formed. So what's the equation? Now this is the equation that's balanced. Now potassium hydroxide is KOH. Potassium hydroxide is aqueous because it's an alkali. Okay. And hydrogen gas, remember, is H2. Right? Hydrogen gas is H2. Now, this reaction produces lots of heat energy. The heat energy is released to the surroundings. Once the heat energy released to the surrounding, it will cause the hydrogen gas to actually catch fire and explode. Okay, this is very crucial. Now, besides that, potassium itself will start burning. It burns with a lilac flame. Lilac means purple. So the color of a fire due to potassium is actually purple. All right. And besides that, the potassium hydroxide solution formed is an alkaline solution. So it will turn red litmus paper blue, and universal indicator will turn purple or violet. Because potassium hydroxide is really alkaline, it's a strong alkali with a pH value of around 14. So at this pH value, universal indicator will turn purple or violet. Okay, and that's for potassium. Now we move to sodium. Sodium is below potassium in the reactivity series. Hence, sodium is slightly less reactive. So below in the reactivity series means less reactive. So sodium is less reactive, so it's not very violent, it's just violent. So sodium floats and reacts violently with cold water. And this again forms the hydroxide. It's sodium hydroxide. So if so again, we need to balance the chemical. Again, the equation for sodium is balanced in a very similar manner to potassium. It's very similar. The coefficients are 2, 2, 2, 1. 2, 2, 2, 1. All right, so the coefficients are the same. The coefficients are the same for a good reason, simply because potassium and sodium, they are both from group number 1. They form K plus, Na plus. They have the same charge in their ions, and therefore the formula of the compounds are the same. Because the formula are the same, the equations will be balanced in the same way with the same coefficients. Okay? Now, sodium is slightly less reactive. So the hydrogen gas may catch fire. It's not a sure thing. It may catch fire and explode as well. Now, sodium hydroxide itself is alkaline. Hence, it will turn red litmus paper blue. And again, universal indicator purple or violet. Again, sodium hydroxide is a strong alkali. Therefore, the pH is 14. Okay? So now we are gradually moving down. Potassium was very violent. Sodium is violent. Now we move down one notch. Calcium is below sodium. So calcium is slightly less reactive than sodium. So what is one level below violent? You need to learn these adjectives and adverbs. So one level below violently is readily. So we say that calcium metal reacts readily with cold water. Readily means moderately. It's in between. Not too slow, but also not too fast and violent. Moderate. So it reacts readily with cold water to form, again, the hydroxide. So it's calcium hydroxide and hydrogen gas. Now here you're going to be careful because calcium is not in group 1. Calcium is from group 2. Hence, the equation you expect should be balanced slightly differently. So this is the equation. Calcium hydroxide is CaOH2. Again, this is aqueous plus hydrogen gas. Now, CaOH2 is calcium hydroxide because Ca2 plus OH minus. Remember, you need a bracket around the OH because it's a polyatomic ion and you got 2 OH minus. Now, CaOH2 calcium hydroxide solution has a special name. And this name you actually already know. It's called lime water. All right. So lime water is actually aqueous calcium hydroxide. Okay. And lime water, of course, is the solution that you use to test for carbon dioxide gas. You bubble the gas into lime water. So what you are doing is you are bubbling the gas into aqueous calcium hydroxide. So now you know lime water is the same as aqueous calcium hydroxide. That's the chemical name for lime water. Okay. Now, lime water or calcium hydroxide is alkaline. So it will also turn red litmus paper blue and universal indicator blue or purple. Now, here there's blue because it depends on the concentration of calcium hydroxide. Calcium hydroxide is not as strong and alkali as sodium hydroxide. So calcium hydroxide can sometimes have a pH of 10. At pH 10 is blue with universal indicator. Okay. Now, finally, we come to magnesium, which is one notch below calcium. So magnesium is below calcium in the reactivity series. Remember, in the reactivity series, so when you memorize the reactivity series, you need to memorize the positions. Okay, you couldn't deduce this from the periodic table. The periodic table doesn't have the reactivity series. You got to memorize it. So magnesium is 1 position below calcium in the reactivity series. This means that magnesium is even less reactive than calcium. So magnesium reacts slowly with cold water and it forms again magnesium hydroxide. And the key thing here is the magnesium hydroxide that's formed is actually a solid. So the state symbol is S for magnesium hydroxide. So please pay attention to that. Now, why is magnesium hydroxide formed as a solid? It's formed as a white solid precipitate because it's insoluble. So the word precipitate means it's a solid which is insoluble in water. So magnesium hydroxide is insoluble in water. And therefore, magnesium hydroxide is not considered an alkali. Alkalis must be able to dissolve in water and dissociate to give you OH minus ions. Magnesium hydroxide doesn't dissolve in water. So magnesium hydroxide is not an alkali, it's a base. It's a base because it's a metal hydroxide, which can still react with acid. Okay, but it's not an alkali. So if you didn't know what's the difference between base and alkali, that's chapter 8, acids and bases. Please go back and revise base versus alkali. That's in chapter 8. Now, a useful exercise at this juncture is also to revise redox at chapter 12. Very often, we will ask you to write these equations for metal plus water. After writing these equations, we will ask you, so which substance is oxidized? Which substance is reduced? Can you use oxidation states to work out for each of these 4 equations which substance is oxidized and which substance is reduced? What is the reducing agent? What's the oxidizing agent? So now your task, you may wish to pause the video here for a short while. Look back at these 4 equations and now try to work out what is reduced, what is oxidized, what is the reducing agent, what's the oxidizing agent. Try working this out in terms of oxidation states. Okay? Now, I hope you have been revising all these chapters and making links between these chapters. Now we shall move to the last reaction for this video, which is metal plus steam. Now, many students are confused about steam. What's steam? How do you form steam in the first place? Steam is formed when you boil water. So you put water into a kettle and boil it. When it boils, the water turns into a gaseous state, right? So the idea is steam is very hot water. Steam must be at least 100 degrees Celsius, if not higher, right? So this is a high temperature. What does this high temperature do? What effect does high temperature have? 2 effects. Number 1, at high temperature, what can you say about particles and atoms? At high temperature, particles have more kinetic energy. That's what you have learned in Sec 1, as well as under kinetic particle theory again in Sec 3. High temperature, particles have more energy. So the particles move faster and more vigorously. And therefore, the reactions become faster and more violent. The second impact of the higher temperature is it forms the oxide. It forms the oxide, not the hydroxide. So metal plus steam forms the metal oxide plus hydrogen gas. Okay, so the key word here is oxide. It's very important to take note of this. All right. Now, so which metals are able to react with steam? Well, shown here is magnesium, zinc, and iron, right? So let's circle magnesium, zinc, and iron. But since I've already circled these three metals, do you think aluminum doesn't react with steam? Looking at the position in the reactivity series, what would you deduce about the reactivity of aluminum with steam? Aluminum is above zinc and iron. So if aluminum is above zinc and iron in the reactivity series, aluminum is more reactive than zinc and iron. If zinc and iron can react with steam, aluminum also can react with steam. It is just that it is not usually described in textbooks. Aluminum can react with steam. All right. And you can deduce this because it's above zinc and iron in the reactivity series. Hence, it's more reactive than zinc and iron. Then how about potassium, sodium, calcium? Do they not react with steam? Are they unreactive? Well, they cannot be unreactive. You have learnt that potassium, sodium, and calcium, they occupy the top positions in the reactivity series. This means that they are super reactive, very reactive. In fact, they are so reactive, they are actually explosive with steam. And because it's explosive, it's not safe to carry out in the laboratory. And therefore, we do not usually react sodium metal with steam. Even though it will react to form sodium oxide and hydrogen, we don't do it. It's unsafe, it's explosive. Okay, so we shall begin our study of metal and steam reaction with just magnesium. So magnesium reacts violently with steam. So you saw just now, magnesium with cold water is slowly, but yet now with steam, higher temperature, that makes all the difference. Now magnesium reacts violently, vigorously, and this forms magnesium oxide and hydrogen gas. So the equation with state symbols is this. Now steam is gaseous water. So it's H2O gas. This is steam. Okay? And this forms magnesium oxide as a solid. Very important to note is the oxide and hydrogen gas, H2. Now, magnesium is quite interesting because when magnesium reacts with steam, it tends to glow. And when magnesium burns or glows, it produces a dazzling white glow. It resembles fireworks. So fireworks main components actually magnesium metal. All right. Now next we move on to zinc. Now zinc is one level or actually two levels below magnesium. So you can deduce that zinc is less reactive than magnesium. And therefore zinc doesn't react violently. One level below violent is readily. So zinc reacts readily with steam to form zinc oxide and hydrogen gas. So again, remember it's the oxide that's formed. So zinc solid plus steam. Steam is H2O gas. Remember state symbol. ZNO solid plus H2. So H2O is a gas. Let's remember that. Now, zinc oxide is formed in this reaction because it's metal and steam. Now, zinc oxide is quite interesting because it changes color when it cools down. So when it's hot, zinc oxide is yellow. Yellow when hot, but it will turn white when cool. So like I said before to all of you, color changes are very important to learn well in chemistry. This is another one of those color changes that you must learn. All right, so add this to your list of color changes. Zinc oxide is very, very unique because it's one of the very few solids which change color upon cooling. So at high temperatures, when it's heated over a Bunsen burner, for example, it's yellow when hot. However, if you left it to cool on the test tube rack, it will turn back to white. Okay, so that is very unique to zinc oxide. And finally, iron. Iron is below zinc. So iron is even less reactive than zinc, and hence iron needs to be heated to a red hot temperature. Red hot means very hot. The iron must be heated constantly, very hot, until it can react. Without heating, the iron just will not react. So this tells you that this reaction is very slow with steam, and it forms iron tetroxide. Now, what on earth is iron tetroxide? This equation you do not need to know, but I'm including it for extra information. Now, iron tetroxide has the formula Fe3O4. So this over here, Fe3O4, is iron tetroxide, which has an interesting oxidation state for iron. All right, if you were to calculate it, what's the oxidation state of iron in iron tetroxide? It's quite an interesting exercise. I would advise us to try it out. All right, but the idea here is that this reaction is very, very slow, and the iron must be heated constantly for this reaction to continue to proceed. In fact, this reaction, if I may write the arrows correctly, is actually reversible. All right. And that's another reason why you need to heat it up. If you don't heat it constantly, you may not form a very good yield of iron tetroxide. All right. So, in summary, we have learned the reactions of metal with cold water. Metal with cold water forms the metal hydroxide. Okay. But metal with steam forms the metal oxide. In both reactions, the gas formed is hydrogen gas. Hydrogen gas is always formed with metals. Now, after remembering the reactions, the next thing to remember is which metals react with cold water, which metals can react with steam. And this is where the chart on the right hand side of the page comes in handy. You should have circled which metals react with steam. All right. Now, I understand there are some questions that follow. We are now going to go through the questions that follow on the next page. Now, this is actually the setup for the reaction of metal with steam. As you can see, the hydrogen gas is collected over here. Now, this method of gas collection, you might recall from chapter 1, we learned gas collection methods. Now, this method of gas collection is called, because it involves water, a trough of water, this is called displacement of water method. Now, displacement of water is very commonly used to collect gases like hydrogen. Why? Why is hydrogen usually collected by displacement of water? This is because the gas hydrogen is insoluble in water. It needs to be insoluble in water. If it dissolved in water, the hydrogen gas will be dissolved and it will never be able to be collected. All right, so that is the idea behind this particular method of gas collection, which is a good link to draw between this and chapter 1. If you have forgotten this and the other methods of gas collection, please revise chapter 1. All right, now let's ponder over the 4 questions below. Number 1, it is not recommended to react potassium and sodium metal with steam. I'm sure you know the reason why. Because they react explosively with steam. Calcium as well, actually. So it is unsafe or dangerous to carry out. All right, next question. Zinc metal does not react with cold water. If you recall, to react with cold water, it must be one of the top 4 most reactive metals. Zinc is not one of the top 4. So zinc doesn't react with cold water, but zinc reacts readily with steam. So why do less reactive metals react with steam? Obviously, it has to do with the temperature. So we started off this section talking about steam, right? Steam is at a higher temperature. So particles have more energy to react. Okay, so there's more energy for the reaction to actually occur. Now, question 3 is a question for us to ponder over. It has never been tested, but I think we should know the reason. Now, you notice I kept stressing that metal with steam, metal plus steam must form the metal oxide. This is very important. But why? Why is it that when you use cold water, the hydroxide, OH, is formed? Why is it that under high temperature, steam, the oxide is formed instead? Again, it has to do with high temperature. And this is crucial. At high temperature, the hydroxide is unstable. What does it mean? It means that it will decompose to form the metal oxide. So the OH can break down to form the oxide, okay, at high temperature when heated up. Now, this is actually a rule, okay? Everything, all metal compounds with oxygen in them will decompose to form the oxide when heated, all right? Most of the time, anything with oxygen in it, whenever you heat it up to a high temperature, it tends to decompose to the oxide. There are some exceptions, okay? But those exceptions are few and far between. So it's not just a hydroxide. If let's say you had a carbonate such as calcium carbonate, it will also decompose to form calcium oxide and carbon dioxide gas when heated up. Okay, so the metal oxide is always what is formed at the end of decomposition, most of the time. All right. Now, question 4 is about experimental setup. So this is the experimental setup for metal with steam. All right. So you can see there is metal, there's a glass wool soaked in water. Of course, the water will boil to form steam. And there's this delivery tube that delivers the hydrogen gas into the inverted test tube in the water. All right. Now, the delivery tube is very important. You need to actually remove the delivery tube before turning off the heating. Why? If I don't remove the delivery tube, the hydrogen gas could flow backwards because it delivers hydrogen. It could deliver hydrogen into the water. It could also deliver hydrogen backwards, Hydrogen is really light, really low density. It can just float backwards. All right. So it is important to remove the delivery tube because it prevents backflow of hydrogen gas into the tube. Now, why is it so important to prevent backflow of hydrogen gas into the tube? Hydrogen gas is flammable and could explode. Remember, the tube is still hot up. If you don't remove the delivery tube, the hydrogen gas flows backwards, backflow. It's hot, it could catch fire and explode. What does hydrogen form when it catches fire? Now, catch fire means combustion. Combustion means burning. Burning means oxygen gas reacts with it. So hydrogen reacts with oxygen to form not H2O2, not hydrogen peroxide, but water. All right. So it's very important to realize that hydrogen is actually very flammable. Hydrogen reacts with oxygen, it burns in oxygen, it explodes in oxygen to form water. Water is the liquid which is formed at the end of the combustion of hydrogen. And that makes full sense because water is H2O. It's the compound of hydrogen and oxygen. All right. Now, that really brings us to the end of the first lecture video, which takes about 45 to 50 minutes to watch. Besides that, I hope you realize from your previous experience with salts, it is important to pause, take down notes, reflect on what you have taken down, as well as re-watch, because you may not get all the details and understand everything within one try. Besides that, if you go to your OneNote content library under chapter 15, you will see many videos. Right? You will see videos at the side. These are the videos that you should also watch as part of the learning so that you can see what it's like to react the metal with steam or to react metals with cold water. So I would expect all of us to watch my lecture videos and these separate videos found in OneNote at the side of the notes. If you don't know where to find it, it's under Content Library, Chapter 15, Notes. All right? Look carefully and make sure you watch everything and take everything down and reflect on what you have learned. So I wish you all the best and see you in the next lecture video. Thank you.